This is Lab Report 3 for Physics 20-11. The goal of this lab is to analyze the motion of a star orbiting a black hole and using net force to calculate the mass of the black hole. The foundational principle in this lab is Newton's second law, the momentum principle. At multiple instances throughout this lab, there will be a need to use the fundamental ideas from the momentum principle in order to retrieve adequate data. The main concepts of this lab include Newton's second law and the parallel and perpendicular components of the net force. Newton's second law of motion is used to break the components of the net force down into multiple aspects and subsequently solve for unknown variables in this lab. Specifically, we will be using the gravitational force in order to obtain the net force, or dp/dt, of the system. In other words, dp/dt will be utilized. The perpendicular component of the net force is the component that is perpendicular to the parallel motion or the general motion of the object, and it has the capacity to change the direction of motion. On the other hand, the parallel component of the net force is a component that points in the direction of momentum and has the capacity to change the speed of the motion of the object. However, before we begin analyzing this lab, there are a few assumptions that will need to be made. We were given that the mass of the star was 2 × 10⁻30 kilograms, so we must assume that the estimate of this mass is accurate enough to firmly calculate the mass of the black hole. Also, we must assume that the only force included in the net force of the system is the gravitational force, as it will greatly change the mass of the black hole depending on forces involved. Moreover, we must assume that the black hole is in fact located at the origin of the system and does not move while the star is in orbit. After making these assumptions, we will be one step closer to calculating the unknown mass of the black hole. I began this lab with editing the known values before running sets of equations in the code. The star's mass was given to be 2 × 10⁻30 kilogram, and the delta T was given to be a day, or 86,400 seconds. The major edits I've made to this code is shown here. If we were given the initial velocity and final velocity, I found that the initial momentum was the mass of the star times the initial velocity, and the final momentum was the mass of the star times the final velocity. Using what we have just found, I found delta V, or change in velocity, to be final velocity minus the initial velocity, and delta P, or change in momentum, to be final momentum minus the initial momentum. Then I've calculated dp/dt to be the change in momentum over the change in time. Then I applied Newton's second law, or the momentum principle, to show that F net is equal to dp/dt. Moving on, I found dp/dt parallel by finding the unit vector of the direction of the final momentum. Then I multiplied that p hat by the magnitude of dp/dt in order to get the dp/dt parallel. Then I used Newton's second law to find that dp/dt parallel is in fact the parallel net force. In this line over here, I found the dp/dt perpendicular by using the fact that net force, or dp/dt total, is equal to dp/dt parallel plus dp/dt perpendicular. And we use Newton's second law once again to show that the perpendicular F net is equal to the dp/dt of the perpendicular. Over here, I was able to calculate the mass of the black hole by rearranging the values in the gravitational force equation, as you can see over here. Over here, I used the scales of the arrows to show the magnitude and the direction of the several arrows: the net force arrow, the parallel arrow, and the perpendicular force arrow. When I ran the code, I was able to see the orbit of the star around the black hole with arrows to represent different aspects of the force. The orange arrow is the net force, the magenta arrow is the parallel force, and the cyan arrow is the perpendicular force. As you can see, there are 3 moments at which the orbit is shown. The top left image displays the magnitudes and the directions of each component when the orbit begins. The bottom image displays the moment at which the gravitational force is the greatest. The image to the right displays the moment at which the orbit makes a full circle back to its original position. Moreover, through the loops of this code, a lengthy list of the calculated masses of the black hole were listed, and I found the average value to be 1.22 × 10⁻30 kilograms. What does this mean? In this lab, we have defined the basic principles of momentum to be F net equal to change in momentum over change in time. Numerically, these values are the same, yet conceptually they represent different things. The net force, along with its perpendicular and parallel forces, is the sum of all forces, while the rate of change of momentum is used to calculate dp/dt, or otherwise known as its change in speed and direction. If the original black hole was removed and a different black hole was placed, would we be able to determine the mass of the new black hole? Assuming the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole, we would not be able to find the new mass. Because the motion or position of the star has not changed, the value of the gravitational force we solved for the old black hole would remain the same. However, the new black hole has a different mass, meaning that it is not possible to find the new mass with the same gravitational force we have used before. Throughout the course of this lab, we have experimented with code in order to analyze the star's motion, net force, and the mass of the black hole. We were able to adequately calculate the mass of the black hole using the fundamental idea of the momentum principle, where the net force is equal to dp dt, which is also equal to dp dt parallel plus dp dt perpendicular.